Have you ever stopped to think about why a firework explodes in this brilliant, massive flash, but a piece of iron just sits there, taking years and years to rust away? I mean, it's all chemistry, right? But it's like one is on fast forward and the other is in super slow motion. Well, today, we're going to grab the controls and figure out how we can actually control the speed of chemistry. So on one side, you've got these incredibly dramatic, fast reactions, The instantaneous pop of a firework, the quick whoosh of a match lighting up. That's chemistry in a real hurry. But on the other side, you've got these super slow, patient processes. Think about metal rusting, food slowly going bad in the fridge, or even rocks eroding over thousands of years. It's the same science, just operating on a completely different clock. So what is it? What's the invisible dial that lets us take a reaction from a slow crawl to an absolute sprint? That is the big question, and that's exactly what we're here to figure out today.
Okay, so here's our game plan. We've just talked about the difference between fast and slow reactions. Next up, we're going to see how you even measure that speed. Then we'll get our hands on the 4 main control knobs that let us change it. After that, we'll uncover the secret of collisions, and finally, we'll see how you're using all of this chemistry in your daily life.
All right, first things first. Before you can control something, you have to be able to measure it. So how in the world do scientists actually put a number on how fast a chemical reaction is going? Well, it all boils down to this thing called the rate of reaction. And honestly, you can just think of it like chemistry's version of miles per hour. It's a way of measuring how quickly your starting ingredients, we call those reactants, get used up, or how fast your final stuff, the products, are being made over a certain amount of time. And this is where scientists get really clever. I mean, you can't see individual atoms reacting, so you have to look for clues you can see. You can measure how much gas is bubbling out of a beaker, or you can literally put the whole experiment on a scale and watch its mass go down. You can even time how long it takes for a clear liquid to get so cloudy that you can't see through it anymore. It's like being a chemical detective. Okay, now for the fun part, the controls themselves. It turns out there are 4 main factors, 4 main knobs we can turn to speed up or slow down pretty much any reaction. And they are concentration, size, temperature, and something called a catalyst. And here's a little trick to remember them. Just think of the letters C, S, T, and P. Let's dig into what each one of these does. So first up is size, and this is really all about surface area. Picture a solid cube of sugar. A reaction can only happen on the outside surfaces of that cube. But what if you take a hammer and smash that cube into a fine powder? All of a sudden, you've exposed all of that inside area. You have way more surface for the reaction to happen on, and so it goes way faster. A classic experiment shows this perfectly. If you drop some big marble chips into acid, you'll see a slow, steady fizz. But if you take those exact same marble chips and grind them into a powder first, then drop them in, it's a furious, fast fizz. It's the same amount of marble, the same acid, but a completely different speed, just because we changed the surface area. All right, our next knob, concentration. This one's pretty intuitive, right? If you pack more particles into the same space, they're just going to bump into each other way more often. It's like being in a crowded room versus an empty one. And in chemistry, more bumps, more collisions, means more chances for a reaction to happen. So, higher concentration equals a faster reaction. Knob number 3 is temperature. When you heat something up, you're basically giving all its particles a shot of energy. They start zipping around faster, and they start hitting each other with a lot more force. So you get more collisions and more powerful collisions. It's a double whammy that makes reactions speed up. It's exactly why we use a hot stove to cook our food faster. And that brings us to our last knob, the catalyst. You can think of a catalyst as like a chemical matchmaker. It's the special substance that jumps into a reaction, helps it happen much, much faster, and then, here's the crazy part, it jumps right back out at the end, totally unchanged. It doesn't get used up, it just makes the whole process easier. So we've got our 4 knobs, concentration, size, temperature, and catalysts. But why? Why do they actually work? The answer to everything lies in this really elegant and simple idea called collision theory. This is the secret science that ties it all together. So at its very core, collision theory says that for 2 things to react, their particles have to literally smash into each other. Seems kind of obvious, right? But here is the twist. The vast majority of those collisions do absolutely nothing. The particles just bounce off each other like billiard balls.
Only a very, very tiny fraction of all the collisions that happen actually lead to a chemical reaction. So for a collision to actually work, for it to be effective, it has to follow two golden rules. Rule number one, the particles have to slam into each other with enough energy. And rule number two, they have to hit each other in exactly the right way, at the right angle, kind of like two puzzle pieces clicking into place. If you fail on either one of those, you get no reaction. That first rule, having enough energy, brings us to this really important idea: activation energy. The best way to think about it is like an energy hill. Your reactants are at the bottom on one side, and the products are on the other. To make the reaction happen, the particles have to have enough energy to get over the top of that hill. It's like an entry fee. If they can't pay it, they just roll right back down. And this is the magic trick of a catalyst. A catalyst doesn't give the particles more energy to climb the hill. Instead, it creates a totally new path, a shortcut with a much, much lower hill. It's like instead of making everyone climb over the mountain, the catalyst just builds up tunnels straight through it. It's a game changer.
So look at it this way. Without a catalyst, you've got this really high energy hill, and maybe only a few of your particles have enough energy to make it over. But when you add a catalyst, that hill gets a lot smaller. And now, suddenly, a whole bunch more of your particles have enough energy. They can afford the entry fee to get over and react. That's why catalysts are so incredibly powerful. Okay, so let's bring all of this back home. Because you might be thinking this is all just stuff for a science lab. But the truth is, you're an expert at this stuff. You are turning these 4 control knobs every single day, probably without even realizing it.
Think about it. When you chew an antacid tablet, instead of just swallowing it whole, you're using the size factor. You're increasing its surface area so it works faster. When you crank up the heat on the stove to cook dinner, you're turning the temperature knob. And that catalytic converter in your car, it's using a catalyst to quickly change nasty exhaust fumes into much safer gases. See? You're a chemist. So in the end, it all comes back to this one single idea. Whether you're increasing the concentration, or the temperature, or the surface area, or you're adding a catalyst, what you're really doing, what all those knobs actually control, is the number of effective collisions that happen every second. That's a secret. That's what really controls the speed of chemistry.
And that kind of leaves us with one last question. Now that you know about the 4 control knobs of chemistry, what's a reaction in your own life you'd want to speed up? Maybe getting a stain out of your favorite shirt. Or what's one you'd want to slow down forever? Like maybe stopping your leftovers from going bad. The power to control that speed is all about understanding the rate of reaction.